Okay, let's dive right into this. Welcome to the Ultimate Explainer, where we are going to treat your Cambridge Computer Science Paper 2 examination not as some terrifying test, but as a high-stakes heist. Seriously, think of yourself as the mastermind. Your primary target, subject code 9618. Today, we're essentially assembling a crew of cognitive specialists to pull off the perfect answer. And we are going after a very specific, highly lucrative target inside this paper, low-level programming and addressing modes. Now look, I know exactly what you might be thinking. Low-level programming can feel incredibly abstract, right? It feels like you're just wandering through this endless maze of memory locations, binary representations, and obscure registers. It can be super overwhelming. But what if I told you that by simply changing your approach, by shifting away from just blindly memorizing raw facts and instead mastering a highly structured algorithmic strategy, you could systematically extract every single mark available? Because that's exactly what we're going to do. We are going to decode the precise framework that examiners use to grade you, which will completely bypass the common traps that catch out thousands of candidates every single year. So grab your notes, get focused, and let's brief the crew. Now, I want you to really think about the sheer scale of the opportunity we're looking at right now. 15%. That is the approximate weight that low-level programming and addressing modes carry in the total marks for Paper 2. Just let that sink in for a second. 15% is absolutely massive. It is not just a tiny bump to help you pass. That 15% is literally the difference between securing a B and walking away with an A star. It represents a huge chunk of the paper, which makes it the absolute perfect objective for our exam heist. If you walk into that exam hall without a bulletproof, ironclad strategy for these specific concepts, you are basically leaving the vault door wide open and walking away from guaranteed marks. The Cambridge syllabus is super clear about this. They explicitly emphasize that top-performing students don't just memorize textbook definitions. No, they exhibit a connected, conceptual understanding that they can transfer to totally unfamiliar contexts. That 15% is sitting right there, waiting for the candidate who knows exactly how to pick the lock. And today, you're going to learn how.
So here is our master plan. Phase 1, we establish the Paper 2 target. Phase 2, we secure the core addressing modes. Phase 3, we uncover the top examiner traps. Phase 4, we deploy the method mark strategy. And finally, Phase 5, we execute the deconstruct, solve, and evaluate protocol.
All right, let's initiate Phase 1, the target. It's time to master the core addressing modes. To actually pull off this heist, you need to know exactly, and I mean exactly, how the CPU locates data. This brings us directly to our 5 key targets: immediate, direct, indirect, indexed, and relative addressing. I want you to think of these as 5 completely different security protocols protecting the vault. First up, immediate addressing. This means the data is right there inside the instruction itself. You literally have the cache in hand, no need to go searching. Then you have direct addressing. This one gives you the exact memory location of the data. You have the specific address to the building, you just have to go there. Indirect addressing is where things get a bit trickier. The instruction gives you an address, sure, but when you go there, you don't find the data. You just find another address that points to the actual data. It's like finding a safety deposit box that only holds a map to the real vault. Next is indexed addressing. This one takes a base address and adds an offset from the index register. It's absolutely perfect for iterating through arrays. Think of it like going to a specific hallway, that's your base address, and counting 3 doors down, which is your offset. Finally, we have relative addressing. This involves jumping a certain number of memory locations forward or backward from your current instruction pointer. Now here's the critical part. The syllabus strictly demands that you don't just define these modes, you must demonstrate practical application. You need to be able to extract information from raw binary representations and actually perform calculations based on these 5 distinct modes.
So let's look at what happens when the execution goes totally wrong. We've got 2 rookie students here, Alex and Sam. Let's break down Alex's approach first. Alex sees a question on addressing modes, totally panics, and immediately just dumps every single raw computer science fact they've ever memorized right onto the page. You end up with this massive wall of text, a ton of information, but absolutely zero analysis. It's all superficial breadth without any analytical depth. They aren't actually answering the specific question asked. Now look at Sam. Sam takes a different but equally flawed approach. Sam rushes the execution. Sam completely ignores the specific command word at the start of the question. Whether it says identify, describe, explain, or compare. Sam just glosses over it and writes a highly generic response, entirely missing the specific, unique context of the question. Both of these rookies leave massive points on the table. Why? Because they completely fail to apply their knowledge to the unfamiliar context presented in the past paper. They aren't using algorithmic thinking. They're just guessing.
Before we continue and decode the real strategy to fix these rookie mistakes, subscribe to our YouTube channel Ace the Exams at actheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Assembling the right team is step one of any successful heist, and we want you on ours.
All right, now that we're all assembled, let's pivot to Phase 2, Insider Intel and the Top Examiner Traps.
Pay close attention here, because what we're looking at is highly classified information pulled straight from the official principal examiner reports. The absolute most crucial point is highlighted right here as an examiner alert. Candidates consistently confuse key terminology. Listen, in low-level programming, the terminology is incredibly precise. You absolutely cannot use the word register and the phrase memory location interchangeably. They are fundamentally different things. You cannot mix up the accumulator with the index register. When examiners read an extended response that just throws around these technical terms without demonstrating a clear, distinct understanding of each one, that red pen comes out immediately. They spot a rookie from a mile away. So, the insider tip here is actually really simple, but it is devastatingly effective. Always define your terms before you use them to build your main argument. If the exam question involves indirect addressing, don't just jump into the scenario. Start by crisply and accurately defining what that mechanism actually does and then apply it to the scenario. Doing this proves to the examiner right from the very first sentence that you possess that connected conceptual understanding they are desperately looking for.
Let's drill down even deeper into this intel. We've compiled the top 3 examiner mistakes reported across the board. Mistake number 1. Answers are simply too vague. Writing something like "it moves the data" just isn't going to cut it at this level. You need highly specific technical details. Where exactly is the data moving from? Where is it moving to? Which specific bus is it traveling on? You have to be precise. Mistake number 2. Forgetting boundary conditions and edge cases. When you're explaining a procedural framework, let's say iterating through an array using indexed addressing, what actually happens when you reach the end of the array? Top-performing candidates don't just explain the normal loop. They anticipate these edge cases and explicitly include them in their analysis. And mistake number 3. Ignoring the given context. The exam will almost always present you with an unfamiliar, highly specific scenario. If you just write down a generic textbook definition of relative addressing without directly referencing the specific program counter values or the unique branching scenario provided in the prompt, you will lose marks. You have to adapt your knowledge to the specific target vault in front of you.
Stop scrolling! Subscribe to our YouTube channel Ace the Exams at actheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @AceTheExams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
Welcome to Phase 3, the Master Plan, featuring our absolute secret weapon, the Method Mark Strategy.
Okay, so we've studied the examiner's traps. We know what not to do. Now it's time to introduce the actual solution. This concept brilliantly illustrates how Cambridge actually assesses your capability. In Computer Science 9618, the marks are incredibly heavily weighted towards the rigorous procedural process. Examiners are desperately looking for logical structuring and analytical depth rather than just checking if you got the final binary answer right. This means algorithmic thinking is your ultimate weapon here. It fundamentally requires step-by-step decomposition. Think about it like this. If a question asks you to trace the contents of a register through a whole series of complex addressing mode instructions, getting that final value in the accumulator right might honestly only be worth 1 single mark. So where do the other 3 or 4 marks come from? They are awarded for showing the step-by-step extraction from the binary representation, performing the correct intermediate calculations, and using clear notation at every single stage. You have to show you're working. You have to prove your process to the examiner.
Let's see exactly how this builds in practice. Remember our 2 rookies from earlier, Alex and Sam? Let's transform their flawed work live right now. Look at the vague answer on the left. It points to data in memory. This is the absolute classic red pen mistake. It completely lacks technical depth and ignores the context of the question. Now look at the context-specific answer over on the right. This utilizes the method mark strategy and what we call the PEAL framework, point, evidence, explanation, link. The instruction extracts the base address and applies an offset from the index register for the array. Boom, that is green check marks all over the page. Notice why it works. It specifies the exact mechanism, extracting a base address and applying an offset. It references the specific hardware components involved, the index register, and crucially, it links directly back to the specific context of the question, the array. This is exactly how you turn a vague, zero-mark sentence into a locked-in, full-mark analytical point. Process, evidence, link.
We are now entering Phase 4, execution. It is time to deconstruct, solve, and evaluate.
All right, it's time to bring out the ultimate three-part framework required to confidently apply these low-level concepts to totally unfamiliar contexts. Here is your execution protocol. Step 1. Deconstruct the question. Before you even think about writing a single word, you must identify the given information, decode the command word, and extract all relevant data. Step 2. Solve systematically. You break the complex problem down into logical, bite-sized steps, you select your appropriate data structure, and you execute with perfectly clear notation. Step 3. Evaluate and check for reasonableness. Once you finally have a result, you have to ask yourself, does this actually make sense in the context of the CPU's architecture? Are there boundary conditions you might have missed? Is the number too large for a 16-bit register? This continuous deconstruct, solve, evaluate loop is the absolute hallmark of top-tier algorithmic thinking. It keeps you safe from silly errors.
Let's put this protocol to the test with Challenge 1, the data scan. I want you to imagine you are sitting in the exam hall, staring at a really complex piece of memory dump, just full of raw binary representations. The clock is ticking down. You literally have 60 seconds. What do? Your deconstruction protocol kicks in. You don't panic. You methodically extract the core trends. You look at the opcode and ask, is this indicating a direct or an immediate operation? You select the appropriate analytical framework based on that. You execute the binary conversion with crystal clear notation right there on your paper, and you make sure to label every single step using strictly correct terminology. No vague words, no guessing, just pure precision. This fast, systematic extraction is exactly what separates the masterminds from the rookies.
Moving on to Challenge 2, find the flaw. I want you to look really closely at the sentence on the screen. The index register is added to the accumulator to find the exact memory location. I want you to read that again to yourself and try to spot the missing context or the massive technical error. Have you found it? The fatal flaw here is confusing the registers. In indexed addressing, the offset stored in the index register is added to the base address that is provided in the instruction itself, not the accumulator. The accumulator is simply where the final data will likely end up after it's been fetched, but it is absolutely not used to calculate the physical memory address in the first place. This is exactly the kind of terminology confusion the principal examiner reports warned us about earlier. If you write this, you lose the mark. Precision in your terminology is literally everything in Paper 2.
And here we have Challenge 3. This matrix brilliantly illustrates the ultimate comparative analysis technique. Frequently, examiners will ask you to compare two different addressing modes, like comparing direct versus indirect addressing. Top students don't just write two separate, rambling paragraphs. They use this specific matrix to speed write perfect peel paragraphs under pressure. Look at how it's structured. For similarities, you compare the exact mechanisms of the two modes and provide an evidence-backed link to the scenario. For differences, you contrast how they handle boundaries or memory constraints, and you conclude with their relative importance. For example, you might contrast how immediate addressing is much faster because it requires no additional memory fetch, but point out it's limited by the size of the operand field, whereas direct addressing allows access to full memory locations but costs the CPU an extra fetch cycle. You connect these thoughts using comparative connectives like whereas, conversely, and similarly. Utilizing this matrix guarantees that you hit the exact analytical depth the examiners are demanding.
We've reached Phase 5, the final review. Let's look at the exam blueprint.
We've gathered all the intel and we've rigorously practiced the execution. To bring it all together, here are the 3 ironclad rules that will guarantee you top marks when analyzing any low-level programming scenario. Rule number 1, decode the command word. Never ever rush this step. If the question says evaluate, you must provide a balanced argument with a solid conclusion, not just a description. Rule number 2, apply the method mark strategy using the peel framework. Every single point you make must have evidence, a clear explanation of the underlying technical mechanism, and a strong link back to the specific context of the question. Remember, prove your process over just stating the final answer. Rule number 3, manage your time via the deconstruct, solve, evaluate loop. Don't just stare blankly at a complex binary puzzle, hoping the answer comes to you. Break it down logically, execute systematically, and always check if your final answer actually makes sense within the physical bounds of a 16-bit or 32-bit system. Follow these 3 rules and that massive 15% is yours for the taking.
The heist is planned, but perfect execution requires practice. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGSE and click that bell. Don't let another exam pass you by.
Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.